Hello everyone, my name is Kunze and I'm a PhD student at RWTH Aachen University. In my studies, I currently investigate how we can use programmable networking hardware to improve network monitoring for large access networks. In this context, I'm particularly interested in what we can do about QUIC, which is also the motivation for this work, where we have investigated how well the QUIC spin bit maps to the Intel Tofino switch. Network monitoring plays a crucial role for effective network management. Yet, it is also a very difficult task, and handling the large amounts of traffic has always been a challenge. The current trend of using programmable networking hardware, however, promises to make things a bit easier. In fact, such hardware has already enabled quite fine-grained monitoring solutions, at least for data center networks. However, these approaches often require control of nearly all of the participating entities and are thus typically not feasible for larger access networks. As a consequence, monitoring in these access networks mostly builds upon passively observing the traffic and thus often observing TCP. TCP measurements in general leverage protocol semantics that can be seen on the wire. For example, the handshake semantics can be used to determine the round-trip time, while sequence numbers and acknowledgements can also be used to determine the RTT as well as packet loss. Related work has further already shown that these concepts can also be realized on programmable networking hardware. Unfortunately, this kind of monitoring becomes more difficult for QUIC, as QUIC protects the required information, or at least the sequence numbers and acknowledgements, which means that only the handshake semantics are in play for measuring the round-trip time. To still satisfy the great need for such passive measurements, QUIC features an explicit measurement signal, and that is the optional spin bit. It basically modulates a square wave signal onto the communication, which can then be used to estimate the RTT of a flow. In comparison to the TCP approaches, the spin bit is a rather simple mechanism, but it is also susceptible to reordering. On the one hand, one could thus think that the spin bit can be easily implemented on a programmable switch, as the TCP measurements have already been shown to work on such platforms. On the other hand, there might be difficulties stemming from the reordering aspect or from QUIC-specific characteristics. Starting off with these considerations, we've set out to track the spin bit on an Intel Tofino switch and, on the way, have looked for challenges that arise from using the QUIC protocol as well as for solutions that can tackle the reordering issues. Our main contribution is a spin bit tracker implementation in P4 for the Intel Tofino switch. You can find the source code if you follow this QR code or the link provided in our paper. Our spin bit tracker consists of several components. First, upon a packet entering the pipeline, we have to map it to a flow, as the spin bit is a per flow mechanism. In a second step, we then have to detect whether a spin bit phase change has actually happened. If that is indeed the case, we can then, in the third step, compute the flow's RTT. In addition to these three core components of our tracker, we've also had to look at several other aspects which we think might help improving the measurement accuracy or how network operators can interact with the measured data. The first thing that we have taken a look at is reordering protection, where we have experimented with two mechanisms in addition to the naive spin phase detection that we've already implemented in the core. We've then also investigated two subsequent post-processing steps. One, a ring buffer, which stores the RTT measurements and basically holds a form of mean RTT, and two, an additional RTT classification step where we can then use the RTT as well as the ring buffer information to classify how stable the measured RTTs are. Finally, we've then also investigated different ways to extract the measurements from the data plane. Overall, our goals in this work were to, on the one hand side, evaluate QUIC-specific challenges for network monitoring. These are specifically represented in the flow identification as well as in the spin phase detection, and then, on the other hand, also provide additional post-processing steps to support network operators. In the following, I would like to first give a short introduction into the challenges of programming for Tofino. After that, I will go over the core components of our approach. And finally, I will talk about the reorder protection and about how our RTT classification can help network operators have a better view on their networks. Please have a look at our paper for more information on these components, as well as the components that I won't go into detail in this talk. To better understand the challenges we face when implementing our tracker for Tofino, I would like to first give a brief overview of the structure of a Tofino switch. The first component of a Tofino is a programmable parser. It is a finite state machine that extracts relevant header information from a packet and makes it available to the rest of the pipeline. The parser can only extract fields of a known length, that is, fixed length fields, or variable length fields with an explicit length identifier. Furthermore, no match action steps can be performed in the parser, so that all operations need to be triggered by the actual packet content. Tofino then has a couple of match action units which can perform table lookups and simple computations, either using the packet content or transforming it. For example, we can do next hop lookups using the destination address. However, these operations are limited to those that can be executed with predictable latency. Multiplications or divisions are thus off the table. Furthermore, there are limits on the kind and number of stateful operations that can be performed on memory that is persistent across packets, so-called registers. For completeness, we finally have a deparser that reassembles the packet. With that being said, let me now get to our spin-bit tracker. The first component of our tracker is the flow identification, which is required as the spin-bit is a per-flow mechanism and thus has to be tracked for each flow individually. For example, the first gray packet could belong to a blue flow, the second one to a yellow flow, and the third one to a green flow. How can we now realize this mechanism on a programmable switch? Well, the first answer to that problem is very simple, as we can just use the traditional 5-tuple for matching. However, QUIC also has an additional feature that lends itself to flow identification, and that is the connection ID. In short, the CID is a variable length identifier which is negotiated during the handshake and then identifies a particular flow or connection. It is especially interesting as QUIC allows for multiple connections over the same 5-tuple, and parts of the 5-tuple may change while the CID stays the same. However, there are also difficulties that we face when we try to include the CIDs on a Tofino switch. The first problem arises from the fact that the short header packets, which carry the spin bit, only contain the variable length CID, but no field indicating its length. As a consequence, the parser cannot know the exact number of bytes to extract. To take this burden off of the parser, we just extract all 20 bytes that might form the CID. In the match action units, we then actually extract the relevant part out of those 20 bytes. However, for this, we also need to know the length of the CID. And as I said on the previous slide, the CIDs are negotiated during the initial handshake. This handshake makes use of long header packets, which luckily contain visible information on the length of the CIDs. Yet, extracting those variable length fields that can range from 0 to 20 bytes is still challenging for Tofino. In fact, using a variable length field, as provided by the P4 language, is not supported in this case due to a specific combination of parser and deparser limitations. Instead, we set up one specific header field for each possible CID length and first extract the CID into the corresponding field. We only later move it to a common field that we can then use in the main pipeline. One thing that I have omitted thus far is the fact that we somehow have to link the CID length, extracted during the handshake, to the short header packet. We consequently require a mapping for which we could, for example, use the 5-tuple again. However, this then directly also raises the question whether all this hassle is actually worth it if we still end up making use of the 5-tuple matching. In the end, our prototype uses the 5-tuple variant as the entirety of our tracker and the CID extraction requires too many sequential steps for bringing it to Tofino. The remaining two core components deal with first detecting the spin bit phase and then calculating the RTT. What you can see here is the basic principle of the spin bit. In essence, the client of a connection always spins the value it has received, while the server just reflects it. Thus, in theory, for each connection there is always exactly one spin flank on the wire, which then travels back and forth between the client and the server. This knowledge can then also be leveraged for calculating the RTT. On this timeline, you can see a spin bit signal, and I've also marked the 2 points T1 and T2 corresponding to the last two spin phase changes. The RTT is then simply T2 minus T1. This simplicity of the spin bit mechanism nicely maps to Tofino, and our implementation essentially only requires two registers, one tracking the spin bit state, the other tracking the last timestamps. Each of these registers holds one entry for each of the tracked flows, and we use the flow ID provided by our first component to access the registers. For timing information, we use a nanosecond resolution timestamp provided by Tofino, which we then scale down to about a millisecond resolution for memory efficiency. Next, we have evaluated whether the measurements on the data plane can keep up with the accuracy of software-based spin bit trackers at the example of SpinDump, a tool developed by Ericsson. For our experiments, we've set up a simple testbed topology. One Tofino switch running our spin bit tracker interconnects one QUIC server and one QUIC client. We perform RTT shaping on the links colored in yellow using the Linux traffic control netm module, and we also deploy SpinDump on the ingress interface of the client. To evaluate the capabilities of our tracker, we've then experimented with different RTTs, download volumes, and readout intervals of the control plane. The following plots show the results for a download volume of 2 MB. We've performed 30 runs in each setting and have calculated the mean RTT as well as 99% confidence intervals. We include RTT numbers provided by QLog, which gives us end-host estimates, as well as the SpinDump measurements. In the plot, you can see the measured round-trip time on the y-axis and the configured round-trip time on the x-axis. The RTT estimates provided by QLog are close to what we've configured on the link. The same holds for the SpinDump measurements, which shows that spin bit measurements in general work, although the measurements fluctuate a bit more. Next, we have the values for our periodic approach. Here the control plane reads out the data plane in 10 millisecond intervals. These values are also close to the ground truth. The same holds for our event-based approach, for which we clone the packet that has triggered the measurements to report the measurement results. While overall this is a rather simple setting, it shows that the approach in general works as expected. Until now, I have shown you the 3 core components of our tracker: the flow identification, a naive spin phase detection, as well as the RTT calculation. Next, I would like to talk about 2 mechanisms to protect against reordering before I will finally present our RTT classification approach. Packet reordering is a known weakness of the spin bit mechanism. Let me quickly demonstrate its impact using the following spin bit sequence. As you can see, there's a lot of reordering in the transition period of this spin bit phase change. In our naive tracking approach, without any protection, each of the packets in that period will trigger one RTT measurement. Thus, instead of a single measurement as it should be, there are now 7 measurements, 6 of which will produce wrong RTT estimates. To solve such issues, we have experimented with 2 protection schemes. The first protection scheme is taken from an internet draft on measurement bits for tracking packet loss. Instead of triggering a phase change upon receiving a first packet carrying the new phase value, we just wait until we've seen a fixed number of packets with that new phase. We also experiment with a second scheme that reuses the same basic idea, but instead of just counting the number of packets with a new phase, we now require those packets to arrive sequentially. After this quick specific component, let me next talk about how we use the RTT measurements and the ring buffer solution, which you can learn more about in our paper, to classify flows. Our main motivation for the RTT classification is to provide network operators a different view on the measurements. For our scheme, we leverage the RTT measurements as well as an accumulator that contains the sum of all RTT measurements currently contained in our ring buffer to classify flow based on the stability of the RTT. Let me explain this using a hands-on view which shows the packet data and metadata that travels along a packet through the pipeline. In the first step, we have a match action table that does the actual classification based on the fresh RTT measurement and the accumulator value. In our example, we have one RTT class for very low RTTs, one target RTT class centering around an average RTT of 40 milliseconds that we label as stable, and for simplicity, a final default entry to capture everything not in those 2 classes. For our concrete flow, we do the matching using the new RTT and the accumulator value, which then classifies our flow as stable. In a subsequent step, we then use that class identifier as well as the flow identifier to actually increment a specific register that counts how many of the readings for a particular flow have been in the different categories. Let me next show you the reordering protection and the RTT classification in action. For this evaluation, we repeat the previous measurement setting, that is a download of 2 megabytes, for a fixed RTT of 40 milliseconds. We then induce 4 unique traffic patterns to test the reorder protection. In the first case, we set the spin bit to arbitrary values. The plot on the left-hand side shows the measured RTTs across the 4 patterns, starting with the first pattern on the complete left, followed by the other patterns. Each column within that plot then contains the 3 types of protection. First, the naive implementation without any protection, then the first protection scheme, and finally the second protection scheme. The same general setup is also visible on the right-hand side, but now the y-axis shows the values of the different counters. In this case, we have one counter indicating reordered packets, characterized by RTTs below 5 milliseconds. We then have one class with correct measurements, centering around 40 milliseconds. And finally, we have a default class for all other readings, which we here label as faulty. If we now take a look at the greasing pattern, we can see that QLock is still able to correctly identify the RTT because it doesn't depend on the spin bit. As to be expected, all the other approaches are far away from the real RTT. However, our classification can actually detect this scenario because all readings are either classified as reordered or as faulty. This shows that even if we cannot compute the correct RTT, our RTT classification is still able to signal that the measurement values are not reliable. The next pattern artificially induces one packet with the old spin bit value after the actual spin phase change has occurred. Taking a look at the RTT calculations, we can see that the naive approach is not able to calculate the real RTT and neither is spin dump. Our 2 protection schemes, however, can effectively protect against this one single reordering. Correspondingly, the register values show a roughly 50-50 share of faulty and reordered readings for the naive variant and large numbers of correct readings for the protection schemes. Pattern 2 basically repeats the first pattern, but for 2 more consecutive packets. Looking at the protection schemes, we can see that the first protection scheme is no longer able to completely protect against this issue, while the second variant can still do so. This also corresponds to the register values on the right. Finally, we have a pattern which induces several consecutive packets of the old flank after the new one. Here, even the protection scheme number 2 is overmatched, and this is also reflected in the RTT classification. Overall, our evaluation scenario nicely illustrates the potential for leveraging both the reorder protection as well as the RTT classification to make sure that the measurements you get are actually sensible. This is now the last slide. Let me briefly conclude what I've shown you today. Our main contribution is a spin bit tracker implementation for the Intel Tofino switch, and the source code is available on GitHub. Our paper entails more information on how we've realized the different components. The main features of our spin bit tracker are first the flow identification. Here we saw that flow identification based on the CID is possible, but quite taxing on Tofino. We have then investigated 2 reorder protection schemes, which seem to work reasonably well. Our RTT classification further showed that there's a lot of potential in post-processing the measurements already in the data plane to make things easier for network operators. For future work, we would love to get a more detailed view on certain aspects of our prototype, for example, the impact of different reordering thresholds. Additionally, we would then also like to dig into how exactly we can leverage the measurements for additional tasks, such as network troubleshooting. Thank you very much.
All right, excellent. Thank you for, again, a very professional presentation. I've been very pleasantly surprised by how good the presentations have been today. Thank you all for that. Are there any questions in the chat? Because we've had some very interesting discussion there already, but if people have any more questions there. For me, indeed, I've recently been doing some work on firewalling. This might have been clear from my question for Nick earlier on as well. And there you have the same problem of tracking or doing flow identification for QUIC streams. And the fact is that you don't know how long the connection ID is. And look at it, try as I may, I can't find a different solution rather than saying the server should share some configuration parameters with the firewall, or in this case, the RTT measurement, so that you know how long individual connection IDs will be. at least if you want to do it efficiently. I don't know if you guys have theorized about other possibilities for that, Ike.
Yeah, not really. So we think, or what we really played with is this detection during the initial handshake, so that we can then capture it. That obviously, but apart from that, we didn't really had an idea how to do it. And that's probably also one of the reasons why this the 5-tuple approach would make more sense in the end if we use that eventually. And I think, as Mirja said, that would probably also make more sense in the context of that a change in the 5-tuple would probably also mean that you probably get a change in the RTT. And yeah, thus we just experimented with how it generally maps at that point, but didn't have any additional ideas how we could get the CID length out of the connection without seeing the handshake.
Yeah, exactly. And then you also have that problem that we discussed in chat about having, because that's something some people might not realize, is that on QUIC you can have multiple QUIC connections sharing the exact same 5-tuple. So client and server can have the same ports. You can run multiple QUIC connections on those because QUIC connections have the CID to be able to demultiplex them. And I wasn't sure how much that would be used, but then Nick said Microsoft will be using that and potentially Apple will too. So again, more challenges for the in-network measurement community.
Yeah, definitely. That will be interesting to see then how this affects the measurement accuracy that we can get. I mean, at the moment, there isn't really that much spin bit traffic to be seen on the internet. And then if then some of those few deployments then actually make use of this multiple connections over the same 5-tuple, so again, reduce the number of maybe sensible readings that we can get, that will be interesting to see how this then really will play out in the internet.
Have you given any thought to the loss bits proposals, and then especially on how difficult those would be to support on something like Tofino?
Yeah, in fact, that's something we're currently working on. And the L bit, so one of the approaches where you basically only have to count the overall number of packets where you see that certain marking that will map very easily to the Tofino. The other ones are a bit more tricky, especially one where you have basically multiple consecutive phases that you have to track. But even so, the T bits, the round trip loss bit, I assume is the full name. But even that, I think we managed to put it on Tofino. And as you've seen in the reorder protection, actually that first mechanism is for the square and the reflection square bits. So those are actually also, or can be supported on the Tofino. So that's a good thing.
That's very good to know. Yeah. Still no questions in chat. I had one more just for me. You nicely mentioned QLog. I like that. I was wondering which QLog events you use. Do you use the real the RTT measurement events, or do you use the spin bit events in QLog and then reconstruct the RTT from that?
No, we use the real RTT measurement events. Yeah.
I was just wondering if there would be any difference there, and if you would use the same algorithm you use on the Tofino on the QLog events, if you would still get the same QLog outcomes. Probably you would, but I was wondering if you did.
Yeah, I mean, that's kind of what we did or I assume that would be somewhat similar to what we see with with spin dump in that case, because we didn't induce any artificial loss until now in the evaluation. So basically what we see in spin dump should also be what actually ends up in QLog. But we'll obviously, or what we want to do next also is to have a look at more network scenarios. So changing RTTs and stuff like that, which we didn't really look at right now because we just wanted to see if it works at all. And now we can see how well it works under more difficult situations.
Yeah, well, I think it's great you've shown the proof of concept to work, because as this goes on, more and more people are going to be watching for that kind of solution for QUIC. And as we discussed, there are so many challenges still to be solved there. Again, something that I think academia can play a big part in helping solve and trying to figure out how that can be done properly. As I feel, and I think Nick agrees with me in the chat there, that we will somehow need to have some kind of communication between QUIC servers or clients and intermediaries in some way to make this type of thing easier or even feasible. And that is going to be interesting.
But even if we assume to get the, for example, CID lengths from the servers, that will still end up being quite tricky. I think we now assume like this larger access network scenario that I mentioned in the talk, because in that context we'll have quite a lot of connections, and then having so storing the per connection or per flow state is already quite tricky on Tofino, and then having that additional information on the different length that we need to keep there will then also put quite some load onto the devices there. So yeah, that's will also be then. So it's also not that easy, even if we have like this cooperation between the devices measuring stuff in the network and the end host, that will make things will open up other difficulties, I think.
Exactly, more stuff we need to solve. So more opportunities for research and development as well. Fantastic. I don't think we have any more questions. Thank you so much, Ike and team, for this work. I'm really looking forward to seeing follow-up papers on this that also do the loss bit and more different scenarios.